Section 6.2. We're going to talk about separable equations and growth and decay. We talked a little bit about separable equations the other day. What were separable equations? What we were able to do with separable differential equations?
Is it when you can separate the dy dx?
We could separate the dy and the dx. So we had very simple differential equations, very simple separable differential equations the other day. I might give you, for example, dy dx equals 2x cubed plus 5x. And what we were able to do, we were able to move the dx over to the other side, separating our variables, and by separating, we mean we got all the y's on one side, we got all the x's on the other side, and then we were able to integrate. So what happens when you integrate dy? You get y equals, what's the integral of 2x cubed plus 5x dx? That's right, 5 halves.
X squared plus c.
Plus c. Very good. 1/2 x to the 4th plus 5 halves x squared plus c. Today we're going to talk about separable equations that are just a little bit more complicated, but the idea is the same. What if you had dy dx equals square root of x over 4y?
Log of both sides? Or natural log of?
I could take the natural log of both sides, but I'm not sure that I want to. I'm not sure what natural log of a derivative would give me. What I'd really like to do is see if I can separate my variables. I could cross multiply, so I could multiply both sides by 4y and multiply both sides by dx. And I would have 4y dy equals square root of x dx. I'm able to separate my variables. I got all the y's on one side, and when I say y, I mean y's and dy's, and I got all the x's on the other side, x and dx. What's that allow me to do? Integrate. So I can integrate 4y dy equals integral square root of x dx. What's the integral of 4y?
Y square root 2. Or sorry, 2y.
2y squared, because you got the 4 in there, equals, what's the integral of x to the 1/2? Two-thirds x to the 3/2 plus c.
So you only put the plus c on the side of the x?
You typically, we only put the plus c on the side of the x. Right, because if I had a, I could put a plus. If I use c over here, I might not use c over here. I might use k, so plus k. But then I could take that plus k. I could subtract k on both sides, and I would still just have a number there. So you could put a number on both sides, but usually we would slide one over and combine them together. Now, if we can, we like to get y all by itself, but for this one, I probably wouldn't, because if I have to get the y all by itself, what am I going to have to do there? Square root both sides. And when I do square root, what happens?
Yes.
You get a mess. You get a plus square root and you get a minus square root. So I would probably leave this one in this form. I would probably leave it in what we call implicit form rather than getting the y all by itself. All right, here's another one. dy dx.
Wait, so it's implicit form as opposed to explicit form, I guess?
Correct. This one is explicit because I have the y all by itself. This one is implicit because I don't have the y all by itself. We prefer explicit form when we can get it. I could get explicit form, but we don't typically like to write the plus minus square root thing, so typically these are left implicitly. dy dx equals 6 minus y. Can't you separate the variables? Yes, how?
Add y and divide by dx.
Add y and multiply by dx?
Yeah.
All right, that's a very common mistake that people will make. Doesn't work because, I'll show you why that doesn't work. If I add y, and there I added y, and now what happens when I multiply by dx? I get dy plus y dx. I've got to multiply that piece by dx too. Have I separated my variables? No, I don't have all the y's on one side and all the x's on the other because of that dx sitting right there. So that's a very common mistake. People will forget that you've got to multiply that one by the dx. So that doesn't work. Multiply by dx and then divide by the whole 6 minus y. That's correct. So dy is 6 minus y dx, and then we divide over. Okay, so quite often you have to divide by something that has a number and a letter in it, 6 minus y. Okay, integrate. I'll integrate the right-hand side. The integral of x dx is, the integral of dx is x plus c. What happens when you integrate the left-hand side? That's a u substitution problem. U is
6 minus y.
6 minus y. So du is
Negative dy.
negative dy. So this becomes negative integral du over u. And what's the integral of du over u? ln u. So this is minus ln u equals x plus c. So that's minus ln, oops, I should have had absolute value on there, shouldn't I? Absolute value, 6 minus y equals x plus c. There's a correct answer. But now my question is, can we get y all by itself? Can we write this equation implicitly? Well, I'm sorry, it is written implicitly. Can we write it explicitly? You could bring this in as a power, and it would drop the 6 minus y to the bottom, or you could simply multiply both sides by negative 1 and get rid of that power also. I think I'd rather do that. So, no, you can't break it apart. The minus is in the inside. If it was ln 6 divided by ln y, then you could. ln 6 divided by y. So I think what I would do is I would take this equation, I would multiply both sides by negative 1. So I'm going to write ln of 6 minus y equals minus x plus c. And we do funny things with the c here in differential equations. Notice I multiplied both sides by negative 1. But c is just a number. If I multiply c by negative 1, what do I have? It's still just a number, isn't it? So we don't usually change the plus c to a minus c. We leave it as just plus c. So technically what I should say is this is really a C1 and this one's really a C2. I changed it, I made it negative. But typically we don't do that. We just leave it as plus C the whole way along.
Is it wrong if we do say minus C?
Nope, it's not wrong. But you're not going to like it, and I'll show you why in a minute here. It's better to leave it as a plus C.
So you only put the C on the side with the x because we only, even though we integrate both sides of the equation?
Correct. Because I could put it on both sides, and I could have like minus ln absolute value of u plus C1 equals x plus C2. But then probably the first thing I would do is subtract C1 on both sides, and then I would just call it C. So typically we only put the c on one side. Truthfully, it doesn't matter which side you put it on. Usually we want to get the y all by itself, so usually we put the c on the same side as the x. That's the way it goes. All right, now I'm trying to get y all by itself here. How do I get rid of this ln? E. So 6 minus y is e to the negative x plus c. We don't need the absolute value anymore. Why not? E to a power can only be positive, so I don't need the absolute value anymore. Good point. And then I'm going to rewrite this. This is e to the negative x times e to the c. That's my property of exponents. And then here we go again with sloppy notation. If c is just a number, what's e to the c? It's a number, so we call it? So we call it c. So we write this as, so that's why you don't want to use that minus sign that you were asking about. We just like to leave it as c. C e to the negative x. And so we're sloppy with our c's here. Our c has changed 3 times, but we still just call it the letter c. And then finally, now I can get y all by itself pretty easily, can't I? I'm going to subtract 6 and divide by negative 1. So negative y equals c e to the negative x minus 6. And then I divide by negative 1. Y equals, what's c divided by negative 1? C. Again, we don't change the value. We leave it as c. C e to the negative x plus 6. There would be my answer to that differential equation. Questions on that?
How do you break that apart? The e to the negative x plus c broke it apart right there.
Why did I break it apart? I broke it apart mostly because instead of having negative x plus c here, I really wanted to just write c out front.
So the same thing.
Same thing, yep. And in just a few minutes here, we'll see why we wanted that c out front. All right, let's do one more of those, and then we'll jump into the word problems. I know you're excited about the word problems. Didn't know there were word problems today. xy plus y prime equals 100x. Well, at this point in your life, the only sort of differential equation you know how to solve is a separable differential equation. So my question is, how do you separate the variables?
Well, we can divide one side. You can divide both sides. Oh, that would give her the
No.
No, it wouldn't, because if I divide by x, I have to divide by x here. I also have to divide by x there.
Subtract xy from both
Subtract
sides.
xy from both sides. That sounds like a good idea.
Then you get what y prime equals, and you can put the equivalent value of y prime into the equation.
You're getting close. Instead of writing it as y prime, I'm going to write dy dx, because I want to get the dy's and the dx's separated eventually anyway, equals 100x minus xy. So notice what you kind of want to do. You want to get the dy dx all by itself on one side, everything else on the other. How does that help? What can you do with this thing on the right-hand side now?
Take out that
You can take out an x. So I take out an x, and I'm left with 100 minus y.
We divide both sides by 100 minus 1.
We divide both sides by 100 minus y. We multiply by the dx, and we have indeed separated our variables. So dy over 100 minus y equals x dx. We've separated our variables. All right, so there's the standard algebra that you have to go through. You get the dy dx alone, everything else on the other side, then typically you're going to be able to factor and then multiply and divide by the appropriate things. All right, we integrate. Integral of dy over 100 minus y equals, I can integrate this side without doing much thinking, 1/2 x squared plus c. What's the integral of dy over to 100 minus y? That's a u substitution problem. U is
100 minus y.
100 minus y, so du is
Negative dy.
negative dy. So this becomes negative integral of du over u equals 1/2 x squared plus c. So that's negative ln of 100 minus y. So I skipped a step there. Instead of writing negative ln u and then plugging my y's back in, I just did it all in one step. Almost exactly the same thing we had last time, isn't it? Again, I want to go through the same process of getting the y all by itself. So what do I have to do to get the y all by itself? Divide by that negative 1. ln of 100 minus y is minus 1/2 x squared plus c. Same trick, I'm not going to change c every time. E's on both sides. 100 minus y equals e to the minus 1/2 x squared plus c. And then I'm going to do the exact same trick as I did last time. I'm going to split that e up. I'm going to write this as e to the minus 1/2 x squared times e to the c. And then e to the c I'm going to call c. So that's c e to the minus 1/2 x squared. Finally, subtract the 100, divide by the negative 1. We get y equals c e to the negative 1/2 x squared plus 100. There's the solution to that the general solution to that differential equation. Questions on that?
Will you give us instructions if you want us to take it all the way to the y equals and not just stop after the implicit?
The truth is, when you go to take your test, the directions will be solve the differential equation. If you stop right there, you have solved the differential equation, and I will mark that as a correct answer.
Could we get bonus points on each question if we were to take it to the y?
Could you get bonus points on each question if you took it all the way? No, I don't think it works that way.
Okay. Worth a try.
That's fair to ask. Can't hurt to ask. The truth is, the reason I went through this a couple times is because what we're going to do with the word problems. We're going to develop a general formula here. So here's what's going to happen in this section. In many situations, the rate of change of an object is directly proportional to the current amount. For example, you take your money and you deposit it in the bank. What does the bank do?
Compounds interest.
They compound interest. They give you interest back. If you have $100 or if you have $100,000, which one earns you more interest? The $100,000. How come?
Compounding a higher principal.
Because you're compounding against a higher principal. That's exactly what I'm saying here. The rate of change. What's the rate of change? What?
How much your money grows.
It's how much your money grows. So how much your money grows is directly proportional to how much money you deposit in the bank. The same thing tends to happen with population. If you have a large population, the population tends to grow very quickly. Whereas if you start with a small population, the population tends to grow more slowly. Slower? More slow? I don't know. Anyway, let's use some symbols. Rate of change. What's a symbol for rate of change?
dy dx.
That's derivative, dy dx. Is, that's equals, directly proportional to the current amount. What does directly proportional mean? It's in the numerator, yes. Typically we use k here. Directly proportional means it's k times something, where inversely proportional would mean it's k divided by something. So it's directly proportional, it's k times something, the current amount. Not e to the whatever. What's our current amount?
P.
No. Our current amount is y, because we said we're using dy dx. So y is the amount that's changing, dy is our change, so y is the current amount. So notice what you end up with there. You end up with a separable differential equation. How do you solve the separable differential equation? Divide by the y, multiplied by the dx. So dy over y is k dx. You integrate both sides. What's the integral of dy over y? Natural log of y. What's the integral of k dx? Not dx. K is just a number. What's the integral of a number?
0.
That's a derivative of a number.
Kx plus c.
The integral of a number is k times x. So that's kx plus c. Get rid of the ln. Y equals e to the kx plus c. And here we go again with the same trick we've done over and over again now, right? This is e to the kx times e to the c. But e to the c is c. Anybody ever seen that formula before? Quite often you've seen it written this way. A equals P e to the RT. The exact same formula, different letters. What's that formula used for? Growth of what? Money. It's continuously compounded interest. That's right. What else do we use it for? What's that? It's used for bacterial growth. This is the formula you used in the first lab for cancer growth. When R was a positive number, those were the cells that were growing. And when R was a negative number, those were the cells that were dying. That's where that formula came from. It wasn't just some formula that I made up. It comes from a differential equation. All right, so here's the so basically we're going to not solve this differential equation every time. We're just going to use this formula over and over again. So here's the sort of problem you might see in your homework. In 1995, the population of Concordia, Kansas was 1,968 people. By 2000, the population was 2,158. Assuming continuous growth, what is the population today? All right, well, we use our standard formula, A equals P e to the RT. In this formula, what does P stand for? Anybody know? It's the initial population. Why is it the initial population? Well, because if I plug in time 0, if t is 0, what's e to the 0? 1. So if I plug in 0, I get e to the 0 here, so I get a equals p. But when I plug in time 0, that means my population at the beginning. So what was my population at the beginning? 1968. So p is 1968. A equals 1968 e to the RT. Next, I need to figure out the value for R. Any thoughts on how to figure out the value for R? We started in 1995, and then we were told something about the year 2000. How many years is that? That's 5 years have gone by. So when time is 5, the population is now changed to be 2158. So we plug that information in. We're going to have population as 2158 equals 1968 e to the R times 5. And then we need to solve that equation. And that'll give us R. How do you solve that equation?
Divided by 1968.
Divided by 1968. So we have 2158 divided by 1968. I'm going to write that as 1079 divided by 984 equals e to the 5r. And then you said do what? You said do ln. So ln of 1079 over 984 equals 5r. So r is ln of 1079 over 984. And then that whole thing is divided by 5. Now, you might notice what I'm not doing. What am I not doing? Typing that in and giving a decimal. Why not? First off, it's an irrational number. It's long, crazy. The other thing is, as soon as you use a decimal, what are you going to do to that decimal probably? You're probably going to round it off. And then what happens when you round off decimals?
You get inaccurate answers.
You get inaccurate answers later. Especially when you're dealing with exponential functions, because exponential functions tend to grow really, really fast. So a small round off here can actually make a big change in the final answer at the end. So my suggestion is don't round off until the very, very end. Save your accuracy as much as you can. So my final answer, the question that they're asking me for, would be A equals 1968 times e to the ln 1079 over 984 divided by 5 times, and then it asks what is the population today? Oops, can't see that anymore. There it is. What is the population today? Well, we started in 1995. This is the year 2015, so that's 20 years later, so I plug in 20. So now I'm going to use my calculator and I'm going to deal with it. So I'm going to take ln of 1079 divided by 984. And then I'm going to divide that by 5. And then I'm going to take e, I said, e to that answer. And notice I'm using the features of my calculator which don't cause me to have to round off. Calculator keeps all those decimals for me. Times 20. And then finally, I need to multiply that by 1968. So my answer would be 2,845 people. I round it off now because I can't have 0.3 people. Not very likely. This one, it probably wouldn't make that big of a difference if you round it off a little bit, because we're not going that far into the future, 15 years past the year 2000. But if you go much further than that, it's going to start to grow quickly, and that number will change dramatically. So avoid round off. All right, so I have two questions for you. Number one, what's the importance of Concordia, Kansas in 1995 and 2000? No, it has nothing to do with this problem. What was what important things happened in Concordia, Kansas in 1995 and 2000?
Like history?
Yeah, important history.
Probably tornadoes.
Maybe, I don't know. Probably tornadoes.
Does it do with you?
It does have to deal with me. In 1995, I got hired at Cloud County Community College in Concordia, Kansas. And in the year 2000, I resigned and came to Corning Community College.
On the C's.
Not to C's.
Yeah.
Cloud County Community College. So I went from 4 C's to 3 C's. I lost a C. Cloud County Community College in Concordia, Kansas. How
Was
does-
calculus and all of those C's as well?
And I taught calculus there. Yes, I did. So I worked there for 5 years. Then I resigned and we moved here. So it's not that important historically, I suppose.
I thought it was like, I don't know.
Uh,
Not your history.
Not my.
Kansas's history.
It was my history. That's right. Not terribly important. Second question is, I talked about round-off error a minute ago. Does anybody know a good example of where round-off error went very, very bad
In this problem or in general?
in general? Most of you are probably too young to remember this.
Something new to-
Has nothing to do with Concordia, Kansas, by the way.
Something new like space stations, yeah.
It has something to do with a rover that we sent to Mars.
Oh, yeah, they didn't, the unit conversions were all.
Half of the rover was built using the English system, and half was built using meters, feet, so on and so forth. The computer had to talk to each other and convert back and forth. The computer was accurate to 16 digits. But by the time the distance from here to Mars was factored in, the rover thought it was still 200 miles above the ground when it hit the ground. And it went smash-o. That was the end of the rover. So that's a very good example of where round-off error is a bad thing.
So it wasn't actually because they were using two different units, it was because when they converted it, it didn't go out accurate enough?
Yeah, you could look at it that way too. But the real issue was they used two different units, and therefore they had to convert back and forth. And every time they converted, there was a little bit of round off. And round off, you would think round off, sometimes you'd have to round up, sometimes you'd have to round down. You'd think it would cancel out. It tends not to. Round off tends to add up, tends to be cumulative for some reason. Probably, my guess is because between 0 and 4 you round down, but between 5 and 9 you round up, so the 5 and 9 group is bigger. So you tend to round up more than you round down. So round off tends to accumulate, and that's what happened there. It thought it was landing, and it was still, no, other way around. It thought it was still 200 miles above the ground when it hit the ground.
That's
Several $1 million down the drain.
A few years worth of flight time.
Yeah, and a couple of years of flight time to get there. Yeah,
That was,
that was a bad situation.
okay, that was.
All right.
the guy that watched that, I think. Oh my goodness. We're going to want to talk first.
All right, other kind of problem you're going to see. Instead of writing it down, I'll copy it out of the book here. Carbon dating. What do you know about carbon dating?
It's effective up to like 4,000 years.
I think it's effective longer than that. Why carbon dating?
Short half-life.
It has short half-life compared to some other radioactive isotopes. The half-life for carbon, they say it's about 5,715 years. So it's fairly long, but shorter than some of the other isotopes, which have half-lives of millions of years. But why use carbon?
Most living things.
It's found in every living thing, as far as we know, on this planet. That's why you have courses like organic chemistry. What's organic chemistry? It's carbon-based chemistry. That's right. All life as we know it is based on carbon. So all life, as far as we know, has carbon in it. And so we can use it. Now, with a half-life of being 5,715 years, that means if you start with a chunk of carbon, what's going to happen in 5,715 years? You're going to have half as much as you started with. What's going to happen in another 5,700 years? Half of that, so you're going to be down to a quarter already. So in a little more than 10,000, a little more than 1,400 years, no, 14,000 years, you're down to a quarter of what you started with. So you can probably go, I don't know, maybe 20 or 30,000 years with carbon-14, but once you get past that, the amount left is going to be so small you won't be able to use it. And so they do use different types of isotopes to try to determine how old dinosaur bones were. Carbon-14 wouldn't work. There's not enough left of it after millions and millions of years. All right, so let's see what this says. It says, carbon-14 dating assumes that the carbon dioxide on Earth today has the same radioactive content as it did centuries ago. If this is true, the amount of carbon-14 absorbed by a tree that grew several centuries ago should be the same as the amount of carbon-14 absorbed by a tree growing today. A piece of ancient charcoal contains only 15% as much of the radioactive carbon as a piece of modern charcoal. How long ago was the tree burned to make the ancient charcoal? All right, well, we're going to have our same formula. A equals P e to the RT. What tends to really throw people for a loop on this problem is, how much carbon-14 did we have at the beginning? It doesn't give us an exact value, but you're right. How much carbon-14 did we have in the beginning? We had all of it. We had 100%. So for P, we're going to use 100. We had 100% at the beginning. So that's the thing that tends to throw people the most on this problem.
Because they don't say it.
Because they don't specifically say it. That's correct. We started with 100% of our carbon-14. Then we can find R. We find R by using the fact that the half-life is 5,715 years. So R should be a negative number, absolutely. Why should R turn out to be a negative number? Because we're decaying this time. R should turn out to be negative. So our T is going to be 5,715. What's A going to be? 50. If we started with 100%, half of that is 50%. So 50 equals 100. E to the R times 5715. Divide. 50 divided by 100 is a half. Equals R to the 5715, E to the 5715R. ln on both sides, ln a half is 5715R. So R is ln of a half divided by 5715. We said R was supposed to be a negative number because we had decay. Is that a negative number? Doesn't look negative. I don't see any minus signs. ln of 1/2 turns out to be negative. Remember, ln is negative for any positive number less than 1. ln was positive between 0 and 1, and ln was positive for bigger than 1. So this really is a negative number. It's just kind of a little bit hidden. It doesn't look it. All right, so now we're ready to answer the question. The question was, the ancient charcoal only contains 15% as much. So how old is it? So how are we going to answer the question? A is now going to be 15. So we're going to have 15 equals 100. E to the R number was ln 1/2 divided by 5715 T. Solved the same way. Divide. 0.15 equals E to the ln a half over 5715 T. ln of 0.15 is ln of 1/2 divided by 5715 T. So T is, I grabbed my calculator. What did I do with it? There it is. ln of 0.15 times 5715 divided by ln of a half is 15,642 years, we'll call it. How do they know that there's 15% left? What they did is they took a piece of charcoal from today, and they measured how much carbon-14 was in that, and then they took the ancient piece of charcoal and they measured how much carbon-14 was in that, and they compared the modern one to the ancient one. And from that, they determined that only 15% was left. So that's kind of what they tend to do when they find human remains also. Is they take the bones and they measure the amount of carbon-14 in the bone, the ancient bone, and compare it to the amount of carbon-14 in a modern bone, somebody who recently died.
Is that like a universal number?
The 5715?
Like the carbon in my bone, so like a universal number that they compare it to?
Yes. Yes, the carbon in your bones is in theory exactly the same as the carbon in my bones, because we live at the same time.
So they don't have to calculate it every time?
They don't have to calculate it every time. No, all they have to really do is measure the amount of carbon-14 in the ancient bone. Other questions?
So all the carbon and then on the planet is steadily decreasing. There's no running growth of carbon.
I don't know. That's a very good question. Because what happens, carbon-14, it decays and becomes carbon-12, which is the stable isotope of carbon. So if that carbon is decaying and going away, where's the other carbon-14 coming from? I don't know. It must be naturally made somehow, somewhere, but I don't know the answer to that. That would be a good question for a chemistry teacher.
We'll bring that up to the commish on Friday.
Yeah.
Other questions?